안녕하세요. All right. So I'll go ahead and share my screen. Okay. Is there anyone who cannot see my shared screen? If not, we'll get started. All right, so this is our 5th lecture, I think. So a brief recap, last time what we talked about. So we talked about the tasks, the 2 prediction tasks, hospital readmission prediction and ICU readmission prediction, which were different things. And then we talked about data pre-processing. So for those 2 tasks, how we want to go over different tables and extract relevant information. So we were, I think we covered all of that. And then we were about to get into the MapReduce, and then we were out of time. So today we'll start with MapReduce. And I changed the contents a little bit. So before I was going to talk about the model, when I was going to talk about the modeling side, I was going to touch over 2 approaches, classical approach and deep learning approach. But I thought it would be better if we talked about the common preparation that is required to take those both approaches, and then talk more about in depth about the classical approach, especially logistic regression, which is probably the most popular go-to method in medical domains or any other domains probably, and how to properly evaluate models so that you can properly train the model basically, or to understand how well it is doing to the given task. And then once we've covered all of this today, we'll go right ahead into the deep learning approach on Thursday. All right. Okay, so MapReduce. So before, when I was talking about the how to pre-process the information on the tables, it was mainly kind of like a high-level approach that does not require how to like scale up your data pre-processing pipeline. So especially because Mimic 3 only consists of about 43,000 patients, and in total it has about 50,000 ICU admission records. So it's not that big. Even if you have only one like Linux machine, it doesn't take too much to go over the tables and then pre-process the tables and come up with a feature vector for your patients or for your admissions. But once you once you come up with a task that requires a lot of people, or if you're working with like a large hospital such as Asan Hospital or Asan Medical Center or Samsung Medical Center, they typically hold patients from all around the nation. So all Korean citizens, like once or twice, they go to the like big hospitals in a lifetime. So probably like, so I don't know, 10,000, 20,000, I mean, 10 million or 20 million patient records in those big hospitals. So you can't like go over each tables and then try to pre-process them sequentially, serially, or it's gonna take like a couple of days. I don't know, maybe like a month, depending on how much data you're talking about. So MapReduce is a philosophy that is like right for that type of tasks. So, oh, by the way, is anybody here familiar with MapReduce, or like how familiar they are with MapReduce? Has anybody used Hadoop prior to this class? But you can type that in the chat box. Or anybody's familiar with Spark, Apache Spark? No? Oh, okay. So MapReduce is basically how do I say it? The divide and conquer type of like an approach. So you have a very big data here, and then you split the data into like subparts, and then you can do like some kind of pre-processing on those split data, and then aggregate it or merge it at the end. So here what we're doing is finding a keyword from big data. So we want to find a specific word like maybe in our case like mortality or something like that, or maybe some diagnosis code. So we have very big data, and the thing to understand about MapReduce is in order to efficiently use MapReduce, you need to, you can only use it for tasks that are not that you can securely divide and conquer. So if you think about tasks that is required to work on, to look at, or to be based on the entire data set, you can't use MapReduce. Or you can approximate it, I guess, but still, I mean, what I'm saying is, tasks like searching a keyword is a very easy to divide and conquer. So you have a very big data, or the original data, which is like, I don't know, like 10 terabytes or gigabytes, I mean, petabytes or exabytes, and all you have to do is just split the data into like 100 different pieces or 1,000 different pieces, depending on how many machines you have. And then once you've split the data, you can do keyword search on each bucket or each split, and then find all the matches, and then merge the matched incidents into a single bucket at the last step. So that is like what you can do with MapReduce. This is the traditional way. Like, MapReduce will do this for you automatically, but you can do this traditional way. You can just have a big data, you can split it manually, and then send it to each worker node manually, do the work there, and then aggregate it manually. So you can do this in a manual fashion. Like, you can like design all the steps and do it yourself, but MapReduce will do it for you. So MapReduce, you have an input, and then it'll automatically divide the input or the big data, the original data, into different subtasks, and then that's where you call the map operation, where map operation is an independent task that can be done on each bucket or each split. So that's the map phase. And then once you've done that, once you've done the map phase, you can reduce it into like smaller, like merged buckets, and then finally have an output. So that is why it's called MapReduce. So there's map phase, and then there's reduce phase, and then there you have a final output. So this is a very, very typical example of why you want to use MapReduce, which is word count example. So you have like a humongous text data, and then you want to count how many times each word or each token occurs in the given data. So here we have a text data called deer, bear, river, car, river, deer, car, bear. So the final output should be like this. Like, bear occurs 2 times, car occurs 3 times, deer occurs 2 times, river occurs 2 times. And the classical way of doing it is just like here. Classical way is maybe you cut it line by line, and then send one line to some worker node, and then that worker node will do like grep or search keyword, and then it'll have its own like occurrence, the frequency table. Like in the first line it had deer once, bear once, river one, car two. In the second line, car 2, river 1, something like that. So there will be like matches, there will be like frequency tables, and then once you have them, you can manually call them into a single node or single machine, and then do the aggregation. But MapReduce will do it for you. So how it does is, first it splits the data, and how you split it, you need to define it. Like, you want to split by every line, or you want to split by like every 10 line. I mean, like you want to split by 10 lines each, or 100 lines each, or maybe file by file. It doesn't, it's very flexible, but you need to define it. And then the whole MapReduce operates on the notion of key and value. So here, obviously, the key should be the word, because we want to count how many times the word occurs in the entire data. So each word will be the key, and then each occurrence, the number of occurrences, will be the value. So as you defined, like for example, let's say we defined that we want to break it down into one, like a line by line. So the first line will go to the like worker node number 1, then worker node number 2, worker node number 3, and then each worker node will count, like tokenize the text, and then count. So this part you need to, the counting part you need to implement. So you need to implement that part, the mapping part, and then once you implement it, the whole MapReduce framework will send the code that you implemented into each node, each worker node, and then run it there locally. So once you run it, it'll be like a table, like a frequency table, like deer once, bear once, river one, car one, river one, deer one, car one, bear one, like this. And then there's a phase called shuffle, where you shuffle the key value pair, and use the key to aggregate it. So here you can see that all the bears come to a single node, and then all the cars come to a single node, all the deers come to a single node, all the rivers come to a single node. So, and basically you append, there's a list of occurrences, and you append each value to a single key. So car, there's car one here, and car one here. So it'll be car 111. There's deer one here, there's deer one here. So there will be deer list consisting of 1 and 1. So shuffle phase is where you like merge the mapped result or the outcome. And so once you've shuffled it, then you need to reduce it. So by reduce means this is a list of occurrences or list of like outcome. And then you basically we're just counting the words. So all we need to do is just sum up the list. So it'll be 1 1 becomes 2, 1 1 1 becomes 3, 1 1 becomes 2, 1 1 becomes 2. And then finally you want to send all those into a single like a single dictionary or a single frequency table and see it for yourself. So this is you just aggregate it into a single list. So before it was looking like that, it looked like this. Now it looks like this. And you can see that the number of map operations or the nodes that do map operations and the number of reduce operations vary. Here we're using only 3 worker nodes, but here we have 4 worker nodes. Or, I mean, it's just an abstraction. Maybe like it'll actually be running on two reduce nodes. Like this 2 things will run on a single node, and these 2 things will run on a single node. It's pretty flexible, but here it's just for showing you the high level abstraction of the actual workflow. So this is the whole gist of MapReduce, and you can think of many different applications or tasks that you want to use MapReduce on. So word count is just like a very simple example, but there are a million other ways. And usually some use cases are that you don't even need to do reduce. All you want to do is just break it down into different like subtasks, and then run your code independently locally, and then aggregate it at the end. Sometimes you don't even need to do like this sophisticated reduce phase. All you need to do is just distributed parallel like processing, and that's it. So it's pretty flexible. All right, so far, any question? So this is the end of like the MapReduce introduction. I'm not gonna show you how to run MapReduce codes using like Hadoop or Spark. That's like the whole other like class for a single semester or even 2 semesters. This is like a very big domain. So any questions so far? No? Okay. By the way, where's my chat box? All right. Okay. All right. No question. All right. So, okay. So a brief like a history. So brief history of MapReduce. So it was developed by Google, and in Google, I think I think they have like a paper and a patent. As far as I know, it was originally developed to construct a inverted index. So if you're familiar with information retrieval or search engine or like search system, you have like millions or billions or trillions of documents that you have in your database, or not just database. Like you have like on like a lot of hard drives, you have like millions and billions of documents, and the user will type in a query, like Google search. Like the user will type in a search query, and then you need to find the relevant documents in like among millions and billions of documents. So it's a very difficult problem. It's hard to pull it off as well as Google. So, and typically what you do is you construct, and you don't just the just because you have like millions or billions of documents and you have a search query, you don't want to go through all the documents to see if individual, like each document is relevant or not. You can't do that. Like, it's going to take like millions of years. So what you do is you construct something called inverted index, which is you have there's like it kind of looks like this. So maybe I can just draw a very simple schematic. So let's see. A search query could be like StarCraft. And then, so this is a single word, and then there could be documents. So each document in your millions, billions of document database, each document will have its own ID. So there will be .id and .id like 1, .id 2, and .id 3, and then some other word like dog. So dog will have .id 2, .id 4, and something like basically like this. This is like millions and billions and millions, and like a lot of like a word and the document ID that the word occurs in. So if the user searches for the word dog in the search query as a search query, then all you need to do is just retrieve document number 2 and document number 4. If the user searches for StarCraft, all you need to do is just retrieve 1, 2, 3, document ID 1, 2, 3, which is like stored in your local hard drive. And if the user searches for StarCraft and dog, like I don't know who would do that, but like for example, let's say I type in StarCraft dog in the search query or that search box. All you need to do is just retrieve. Maybe it depends on like if you're doing AND operation or operation, but if you're doing like OR operation, then all you need to do is just return like 1, 2, 3, and 4, or you need to rank it first, I guess. So because document 2 has both dog and StarCraft, that should be ranked number 1. So it's a ranked list, of course. So like 2 and then 1, 3, 4, something like that. It's very this like information retrieval is a whole another class for like a single semester. Anyway, so this is called inverted index, and you can see it's very, very, very similar to a word count example. So, but Google needs to construct inverted index very, very often because people like upload new stuff to the web every single day, or maybe even every single like second. So you crawl or collect a lot of documents on the web and then store it into your hard drive and then construct your inverted index every hour maybe, or every 30 minutes. And you can't just go like document by document to construct a inverted index because you have like millions and billions of documents. So like MapReduce is the perfect philosophy or framework to do this kind of inverted index construction. So, and it is still used internally. I don't think it's called MapReduce anymore. I forgot what it was called, but everybody, like anybody who needs to pre-process data, or not pre-process, anybody who needs to process data like on a large scale, they use like MapReduce in Google. And they have more sophisticated approach, but the gist, the essence is still the same. Like you break it down into subtasks, you do stuff locally, and then you merge it, and then do aggregation operation there, and then get the final output. All right, so there are, so the MapReduce framework that Google uses is for internal use only. So people have like open sourced MapReduce, which is named Hadoop. So it's an Apache project written in Java. So it's an open source version of MapReduce. And it's based on read writes to local disks. So as I said, you have like a bunch of documents in your local drives, and then you do stuff there, and then you put it out. You put it back there. So it's so once you install Hadoop, it'll form a cluster. Like you can dedicate certain amount of like hard drive space from each box or each Linux machine as a part of like a whole like cloud drive. So whatever once you upload something, once you copy some document into that cloud drive, then the whole Hadoop framework will recognize that it has that document. So it's like the very, very basic form of cloud. So, and I think it was developed by an engineer from Yahoo back in, I don't know, like early 2010, no, maybe late 2000s, something like that. So Hadoop is based on read writes to local disk. So it's a bit slow, And Apache Spark came after Hadoop, and it was developed by Berkeley, and then it became adopted by Apache. So it's Apache project, and it's written in Scala, which is a kind of like a functional programming. So it's a bit tricky to get used to. I'm not even like familiar with Scala, but the thing that Spark shines is it's a MapReduce on memory, so it's way faster than Hadoop. But as a like an infrastructure, like as an underlying file system, it still uses Hadoop's file systems. There's something called HDFS, which is Hadoop data file system or Hadoop file system, something. It's basically what makes the cluster run, and Apache Spark runs on top of HDFS. But the actual operations are done on memory, not disks, so it's way faster than Hadoop. So I heard that a lot of people, I mean, a lot of like IT companies use Spark in the United States. I'm not sure about Korea, but yeah, some people, yeah, some companies, like when they're hiring new employees, they require like Spark expertise for backend engineers, especially who handles a lot of data, basically, right? All right, so this is the end of MapReduce. And so if you're interested in MapReduce, you can start by going and looking for Hadoop and Spark, but it's gonna I don't think we're gonna need it in this class because yeah, Mimic, even like EICU, which is a bigger open source data set than Mimic, is only like 200,000 patient records or something. So we don't need it probably. Right. So what's, oh, it's okay. So this is kind of an example how you would use MapReduce to construct the ICU readmission data set. So before I showed you how to like how to pre-process your data, your tables for ICU readmission. Basically, you go over ICUSTAYS, and then you go over the chart tables, basically the chart events. So you have ICUSTAYS and chart events, and then you like extract information from like chart events, the item IDs and the value numbers and stuff. So, but you can do it in a serial fashion. You just take a table. You just take a table, like a ICU table or chart event tables, and just go line by line and extract relevant information. Or you can exactly do like this. You can break it down and then do it like a divide and conquer style. So how you would do it in MapReduce style is like, first of all, you have a single table called ICUSTAYS. Maybe I should remind you guys of the schema of ICUSTAYS. So, yeah, right. So ICUSTAYS, it has a hospital admission ID, has ICU admission ID, and then it has in time, out time, like the time that you were admitted to the ICU and you got out of the ICU, and the length of stay, which is the amount of time that you were staying in the ICU. So, and you have chart events, which consists of the same, like hospital admission ID, ICU admission ID. Item ID is the thing that you were checked for. It's the measure, the type, like a kind of measure, like blood pressure or your body temperature or O2 saturation level, that kind of stuff. And the value number is the actual measured value for each item. So all you need to do in ICU in the oh, this should be ICU readmission. All you need to do for ICU readmission is you just go through these two tables and then construct a feature vector. And you can do it serially, going by line, or you can do it MapReduce. So you split the ICUSTAYS, and then each ICUSTAY will have a unique hospital admission ID. So you would set the hospital admission ID as a key, and these as the value. Like it's MapReduce is a very flexible framework. So it can be, the value could take any form. Like it could be any object. It could be like a list or a tuple or dictionary or whatever, like any object. So you wanted to extract five columns from the ICUSTAYS table, and so we have one key and 4 values. So 1, 2, 3, 4 values and 1 key. And then once you extract those from the split ICUSTAYS records, then you shuffle it by the key. So it'll be merged as a key and a list, as I said before. So there is a key for each hospital admission ID. The unique ID will be the key, and all the admissions, all the ICU admissions per hospital admission will be appended in like a long list. If the patient actually did go to hospital, if the patient actually did end up in ICU multiple times, then it'll be appended in the list. So, and it'll consist of ICU stay ID and in time out time LOS. Another ICU stay ID, in time out time LOS. So if the patient was admitted to ICU like 3 times, then the size of the list will be 3, basically. And then you reduce it to so hospital stay. So let's see. Okay, so basically when you reduce it into a single like outcome, it'll be like a hospital stays object where it consists of like, so it's a dictionary of hospital stays, and the key will be hospital admission ID, and the ICU ID will be the content. So it's like a nested dictionary, like I showed you in the last time, like nested dictionary, where the high level is the hospital admission, the lower level dictionaries for the ICU admission, and then like the inner dictionary will contain relevant information per ICU stay. So that will be MapReduce plus ICU readmission. And you also need to process the chart events, the actual measures of the patient. So in this case, it's a bit different because before, all you need to, the key was just a single hospital admission ID, because all you cared about is how many times the patient was admitted to the ICU during a single hospital admission. So like the key could be just the hospital admission, but now you care about the measurements that were taken within the ICU, not within the hospital admission. You care about the measurements, the blood pressure, the temperature that was taken during a single ICU stay. So now the key becomes a tuple. Again, it's a very flexible framework. So a key could also be a tuple, could be a key, not just a single like literal like a character, or it doesn't have to be character or float value. Like it could be like a tuple. So, but it cannot be a list, or it cannot be a dictionary if you're familiar with Python. So it can be a tuple. So it'll be a tuple consisting of hospital admission ID and ICU stay ID. So it's like it'll be a unique key, and then the values would be the item types and actual values. So if you've taken like 4 measurements during ICU stay, then it'll consist of a unique key and 4 size 4 list, basically. And then you can reduce it into again, the nested dictionary. So the upper level will be hospital stay, and then the inner dictionary will be the ICU stay, and it'll now consist of the meta information in out time, the length of stay, but it'll also consist of chart items and chart values. So that's how you would do it in a MapReduce style. You like break it down into key values and then shuffle it and then reduce it. So the more machines you have, like the more speed up you'll gain, basically. Like if you have 10 machines, theoretically it'll be like 10 times faster than just working with a single machine. And like 100 machines, of course, 100 times, 1,000 machines, 1,000 times. I mean, it's all theoretical. Once you have a lot of nodes, like it's bound to happen that some nodes will crash, and then you need to turn it up, boot it up again. So like the whole distributed system is a whole another story. All right, so this is the end of the data pre-processing, and we'll jump on to the modeling side. So far, any question? No. All right. Okay, 2 things we'll talk about common in modeling, which is common preparation and classical approach. I hope we can finish all the contents today, because I really want to get started into the deep learning approach tomorrow, Thursday. So we got a lot of grounds to cover. All right, so whichever like modeling technique you decide to use for any tasks, any prediction tasks. Here I gave you like 2 prediction tasks examples. which is hospital readmission and ICU readmission. And for each task, you can take like a lot of different like methods. Like you can do classical like logistic regression, or you can go for like random forest. You can take convolutional neural network, recurrent neural networks, transformer, which is kind of relatively new. Like a lot of different approaches you can take to achieve a single task. But whichever route you take, there's always the same thing that you have to go through, which is, maybe you can think of this as another, like a next step pre-processing. It's another like a kind of pre-processing. So before you actually train a model, or you actually learn a model parameters, it's another step that you have to take. So that's why I just named it common preparation. So typically what you want to do is you want to split your entire data set into a train and test set, or train or train validation test set, or some people call it like development set, like validation set. Sometimes it's called development set. And what you want to do is you basically want to do n-fold cross validation. And oh wait, is anybody here not familiar with n-fold cross validation? Or everybody just like crystal clear with what n-fold cross validation is? Okay, so then I don't have to go through it. Okay, so then I won't cover this. So just like a gotcha or a caveat is that when you split your data into like different train set and test set and do it multiple times, you might want to preserve the positive example, the ratio between positive samples and negative samples. Like people who were actually readmitted to the ICU and people who are not, like if the ratio is like 9 to 1, like 10% of people were readmitted to the ICU and 90% were not, then when you are splitting into train set and test set, you might want to preserve that ratio in like train set and test set. Like you don't want the test set to be like all negative samples. Then it won't really, then you won't be able to properly evaluate the performance of your model, right? And then another thing that you have to do is you have to, this kind of pertains to, I mean, this is kind of only applies to, not only, but so if you're talking, what I mean by string integer mapping is that like if you're dealing with images, then images are already a scale. It comes in a scalar form. Like you have pixel values in 3 different channels, red and RGB channel, and for each channel there's like a matrix, and each element in the matrix is a pixel value, the strength intensity of the pixel. So it's already a numerical value. But here we have all sorts of different types of variables. And so for variables that are not, or features that are not numeric, or like basically like a numeric scalar value, then you need to convert it into a numerical value, because all machine learning models require numerical input. So for example, ethnicity. Like if, let's say you're Asian and your medical record says Asian, you can't actually use that information you can't just feed that information into like a machine learning model like directly. You need to convert it into a numerical form. And so for example, if there are like 4 ethnicities, like Asian, Black, Hispanic, and white, then you can assign random like numerical value to each ethnicity, like integer value. So just random, it doesn't really mean anything. Like 0, Asian being 0, Black being 1, Hispanic being 2, white being 3, doesn't mean anything. It's just some number that you assign so that you can feed it into your machine learning model. But that's what you would typically do. So for example, if we're dealing with hospital admission table, and then you extract relevant information and construct a dictionary, then these times will be numerical value, like admit time, discharge time. It'll be like a calendar form, but you can convert the calendar form to like an integer value, like the epoch from 1970 January 1st, that Linux time epoch. So these are numerical values. Gender is like could be like a numerical value, like male being, I mean, gender is again, like male and female is a string, but you can internally like think of like male as 0, female being 1. So, but these are, the rest of these 3 and these 4 are a bit different. So the red ones are what's called a categorical value or categorical variable, and the blue ones are multi-label variable. So we'll see how we can deal with that. And the last one is the label, because we were talking about like hospital readmissions. So you want to have like the actual true label, which is either 0 or 1, 0 being not readmitted, 1 being readmitted. And so, all right, so the difference between categorical variable and multi-level variable is that the categorical
방금 일어났어. 바로 앉은 거야.
Was that a question?
No, nothing. Sorry.
Okay, all right, so no problem. Anyway, so categorical variable, they can only take one value at a time. For example, you can't be white and Asian at the same time. No, I mean, it's always, anyway, so technically you can't be white and black at the same time. Yeah, so that's what it's called. Why categorical variables are like, you can only be one thing at once, like marital status. You can't be single and divorced. Okay, so it's technical. There's a lot of like technical nuance, but basically, like you can't be single and married at the same time, something like that. So, but multi-label variables are, you can take multiple values at the same time. Like you can have multiple diagnosis codes. Like you can at the same time have fever and headache. There's nothing stopping you from having like a lot of things happening to you at once. And of course, same deal with the medications. You can take multiple medications at a time. Nothing stopping you from taking like Tylenols and ibuprofen at the same time. So you can see what I'm trying to get at here. All right, so this is just like a schema, and this is the actual some hypothetical example that I came up with. So admit time, discharge time, and admit type. So the route or the form that you were admitted to the hospital was like through the emergency room. So ER. So admit type is emergency. Marital status, you're divorced, and ethnicity, you're a white person, and then you're a woman. And the reason for being admitted, as I said in the last class, if people remember, the admission diagnosis is different from diagnosis list. This is kind of like a high level reason why you were admitted to the hospital in the first place. And so it could be like one of many things, and only one of many things. So like chest pain, and then diagnosis list. I think I covered this ICD-9 thing like couple classes back. So this is like ICD-9 code, like 4109, 4280. So this is your diagnosis list, and then this is your medication list. Like during this hospital admission, you've taken warfarin, D5W, and vancomycin. And procedure is also it's a like a CP. Either you use CPT procedure codes or ICD procedure codes, doesn't matter, but it's some form of number or some form of string, like sequence of strings. So this will be your actual like a hypothetical example, and you want this to be converted to this. First of all, you want to map all the strings into a integer, a numerical value. So I guess this should have been some number. I won't change this, but this should be like some other number. And so admit type, like this is all hypothetical. There was a chat. Why don't we just use ICD-9 numbers to numericalize them? So that's a good question. So, all right. So the reason is that ICD-9 numbers don't start from 0 and end with like 9999. It's maybe, let's see. Can everybody see the Safari browser? Because sometimes when I like do when I change the focus, it doesn't really other people can't see it. Can everybody see this, or anybody still seeing the slides? Okay, everybody. Okay, cool. So as I said, the reason that we don't use ICD-9 codes directly as the right. So here, yes, I can see. Okay, cool. So the reason that we don't use ICD-9 codes directly as an integer value or numerical value is that you can see that the very first ICD-9 code doesn't start with 0. It starts with 001.0. So the ICD-9 codes in Mimic 3 is missing the dots. So if you look at the actual tables like ICD-9, the diagnosis ICD table, you will see that it is missing the decimal, the dots that separate between like the higher level information, the fine-grained information. So anyway, so it starts from 0010, 0011, and it jumps from 11 to 19. You don't have like 12s or 13s or 14s. So it's a kind of like a sparsely mapped, sparsely constructed diagnosis taxonomy, or taxonomy. It's not I guess it's not ontology. So it's hierarchical hierarchical diagnosis taxonomy, which is sparsely constructed. So if you use this as a numerical value, you'll be missing a lot of things, and that's just like waste of memory. So all right, I hope this answered the question correctly. So you want to map it, and so typically how you map the ICD-9 codes into a numerical value is you just go through each line in the patient record, and then once you encounter a new ICD-9 code that you've never seen before, then you just like assign a number, like an incremental assignment. So okay, so this is just another hypothetical example that you want this to be this. So you can see all the strings have become a numerical value, like 1, 3, 3, 1, 12. But these are all, as I said, these are all like the number, like this being chest pain and this being 12 has nothing to do with, like 12 and chest pain has nothing to do with each other. It's just random assignment. Doesn't need, as long as you can distinguish between different like values and different values by assigning them like different integer, that is fine. Doesn't really matter. So all right, so once you've done this, or the reason you're doing this is that you want to convert your admission record or admission dictionary into a vector form eventually. Like you want to convert everything into a vectorized format in the end, so that you can feed that vector into a machine learning model. Like it doesn't matter if you're talking about random forest or logistic regression, support vector machine, neural network, doesn't really matter. It has to be a vector form. So you want to convert, so you want to start from here, and then you want to arrive at a vector. And the way you do it is you first convert this into a numerical value, and then you need to, and then you basically convert each numerical value into a vector. So for example, here, what I mean by this here is that, let's say we have total 3 admission types. Elective being that you went to the hospital by yourself. You didn't take ambulance and then get like taken into the hospital on bed. So elective being like you did it yourself. So elective, emergency, and other. So let's say there are total 3 admission types in your data set, and the admit type was emergency was mapped to 1 for some reason. Then you would want to have a vector like this. So dimension 3 being there's 3 admission types, and because it was 1, and we start with 0 index, so the dimension, which is the 0th dimension, the first dimension, second dimension, and you want to fill the second one, the second box as 1. Again, the integer 1 in emergency has no semantic connection. Doesn't mean anything. It's just a number. And the same deal here. So let's say there are 5 types of marital status in your data set: single, married, widowed, divorced, other. And your marital status being divorced was 3, mapped to 3. So you want to hit the index, you want to fill the index 3 with 1. So again, this is 5-dimensional vector because there are 5 marital status types. So you want to fill this as 1. Same deal here. There were, for example, let's say there were 4 ethnicities: Asian, Black, Hispanic, White, and you want the example was that this person was white. So being 3, and we mapped that to 3. So this is, you want to fill the last dimension with the 1, and the other will be 0. So basically, this is how you represent a categorical variable. So you prepare a vector that is the same size as the total number of types of that variable, and then you fill like a single dimension, single coordinate that corresponds to the actual value of that variable. All right. And then admit type, let's say, for example, there were 14 admission diagnosis types, and then this happened to be 12, then you fill the second to the last one dimension by 1. So, and it'll be like 14 dimensions. It'll be 0, 0, 0, 0, 0, 0, all the way up until index number 12, index number 0 being here, index number 12, and that will be 1, and your last dimension again 0. Now, multi-label variables are a bit different. It's not too different. Basically, the same deal. For example, let's say there are 10,000 diagnosis types. That's about how many diagnosis types there are in ICD-9 codes. So let's say there are 10,000 diagnosis types. Then you need to prepare a 10,000 dimensional vector, all filled with zeros. It'll be 0, 0, 0, 0, 0, like all the way. And then because you have index 422, which has nothing to do with actual diagnosis value, it's just you just happen to have 422. You just happen to map them into 422 and 332, 14. So you just prepare a vector of zero vector of dimension 10,000, and you fill the index 422 with 1 and index 3214 with as 1, and then all the others are 0. So basically, this very, very sparse vector is telling you that during this hospital admission, 2 things happen to you, which is this thing and this thing. So it's the same deal with your medication. Let's say, for example, you have 20,000 different medication types. So you prepare a 20,000 dimensional vector filled with zeros initially, and then you fill index number 64, 153, 122 with 1s, and the others will be 0. Again, it'll be super, super sparse. Like out of 20,000 dimensions, only 3 of them are 1s. And the same deal again with procedure. Here. So like if we assume that there are 10,000 procedure types, then it'll be 10,000 dimensional vector filled with zeros, only except for index 2142. So you do this, and so you've prepared a you prepared a lot of vectors, like admit type, marital status, ethnicity, admit type, like admission diagnosis type, like all these were like represented as vectors. Then you concatenate all the vectors. So you take vector from here, vector from here, vector from here, vector from here, like all those vectors, and then just like concatenate it into a very super, super long vector. So so for this is just an example. It doesn't like I just follow the order of the features or the variable names and concatenated them. So the first 3 will be admission type, and as I said, it'll be like 0, 1, 0. The second like 5 dimensions will be marital status. Next 4 dimensions will be ethnicity, and then the 4th will be gender, which I did not show you as a vector because it's a binary value, 0 being male, 1 being female. So I didn't prepare a vector, but when you're concatenating information, you want to include them. So it'll be just a single dimension consisting of like either 0 or 1. And then after gender, there will be like 14 dimensions of admission diagnosis types. Then there will be like, after that, there'll be 10,000 dimensions of diagnosis list, another 20,000 dimensions for medication list, and then another 10,000 dimensions for procedure list. So it'll be like super, super long vector. Like the exact number will be like 3 plus 4 plus 5 plus 4 plus like 1 plus 14, like the total number of types per variable, like 3 admission types, 5 marital status types, 4 ethnicity types, and just this doesn't mean that there are only one gender type. It's just that you only need one vector or one dimension to represent a gender. Then 14 admission diagnosis types, 10,000 diagnosis list types, something like this. You can see where I'm going to. So it'll be like at least 40,000 dimensions, which is very, very long. So you can call this a admission representation vector. The entire 40,000-ish, 40,000 dimensional, approximately 40,000 dimensional vector will be a vector that represents this particular hospital admission. Oh well, I've excluded the admit time, the discharge time, and the readmission label. I forgot to put them here somewhere. Like here will be some admission time dimension here, discharge dimension here, and readmission label somewhere here. But basically, this is the like a numerical representation or vectorized form of your hospital admission. All right, so next, so far, any question? This is pretty straightforward, right? Like you just convert everything into numerical value and then prepare them into vector form, and then that'll be your representation vector. And so up to now, this was hospital admission. You can also do the same thing to ICU admission. So before it was in time and out time and length of stay, item list, like the blood pressure, like 42 could be like, I don't know, urine analysis, and like 891 could be temperature. So during your ICU admission, you take temperature 2 times, and like you take blood pressure 3 times, like 1, 2, 3, and this could be something else. So, and each measurement will have a corresponding value. So this ICU admission representation, ICU admission is a bit different from hospital admission because now we have scalar variables. Before we didn't have a scalar variable. I mean, we didn't have like a list of scalar variables. It was just like it was all discrete variables. It's either like ethnicity or gender or diagnosis types or medication types. But now you have actual continuous measures, the values from like taking measures. So it's a bit different. So the way you do it is that typically what you would do is if you follow the same approach as before, like if you follow the same approach that I've taken when I was like preparing a vector to represent the hospital admission, then there's like you run into a conflict. So, oh, I'm sorry. These should be, I guess these should be blue. Okay. Because now before, if you want to represent this as like a multi-label variable, like the diagnosis list or medications list or procedure list, then you have for example, let's say you have 15,000 item types. Like there are 15,000 different ways different types of measurements. And so you prepare a 15,000 dimensional vector, all filled with zeros first. And then you start filling with like, you set the index number 42 to 1. Then you set the index number 891 to 1. And then you run again into 891. And you don't know what to do because you've already filled this value with 1 before. But now you run into another one. And maybe you want to set it to 2 because it occurred twice during your ICU admission. And you may want to set this to 3 because this happened 3 times during your ICU admission. But the problem is each measure has different scalar values. So what are you going to do now? Like, are you going to sum them up? Like 68 plus 72 being 140. Like, that is probably not a good idea. You don't want to just sum your measurements up and then put them into a vector, which is probably not the most optimal way to represent your ICU admission. So do you want to maybe average? Like 68 plus 72 divided by 2. And these 3 numbers, like average, there will be like, which will be like around 102 or something. So that is one way to go. Or if you have prior knowledge about what's important and what's not, like for example, if you're taking temperature and you only care about the maximum value, like you only care about the fever, then maybe you can take the max operation. Like you look at these two and then you only take 72, and you look at these three numbers and you only take like 102.8, something like that. That's another way to deal with like repeated measures. So that, yeah, basically you need to come up with a way to properly convert your ICU admission into a vector representation. And the good thing about neural networks, especially recurrent neural networks, is that it can take arbitrary number of measurements. Like it doesn't matter how how many like repeated measures you have, doesn't really matter, because you can sequentially feed them into a recurrent neural network, or RNN. But if we're taking the classical approach, then there's not, I don't think, as far as I know, there's not really a great way to feed repeated measures of different scalar values. All right, but anyway, so it's like the designer's decision. It's your choice as a machine learning like researcher or engineer or data scientist. It's up to you how you want to handle these multiple occurrences of different scalar values. I think I would say probably what you want to do is you want to take the latest, the most recent measures, because each measure will actually have a timestamp attached to it, because you take temperatures or blood pressures over time. So you might want to take the latest value, the most up-to-date value, or maybe you want to average them. That's probably a good choice too. So another thing that you want to consider is that these, up to now, we were talking about the single ICU admission or single hospital admission, and you can convert them into like a fixed size vector, like 40,000 dimensional vector, or maybe here, like 15,000 dimensional vector, because of all the item types. But once you have them and you want to model a longer dependency, basically so these blue strips being the hospital admissions, and each hospital admission can be converted to a vector, like this. So this individual vector, there will be like a one-to-one mapping from each hospital admission to like a 40,000 dimensional vector. And once you have them, and maybe sometimes you want to model, maybe sometimes you want to construct a patient representation vector, not hospital admission representation. You want to obtain a patient representation, so patient consists of multiple hospital admissions over time. So some patients can have 2 hospital admissions, some patients can have 3 hospital admissions, some patients can have like 10 hospital admissions. So it's like the number varies patient by patient. So how you want to handle that to obtain a patient representation vector? Like you want to capture a longer dependency, like you want to capture a information spanning over 10 years or 5 years, something like that, not just one hospital admission. In that case, and that's typically required for patient level prediction tasks, not the hospital level prediction task, like whether the patient will die during the hospital or whether there will be another readmission. But you want to like model a chronic disease, like heart failure or hypertension or kidney failure, that kind of like a disease that lasts for like a very long time. So if you want to model that, if you want to predict that, then you probably need patient level information. And how to derive a patient representation vector is, again, it's designer's choice. So maybe you can sum all these vectors up, like individual hospital admission vectors. You can just add them all up, and then it'll still give you like 40,000-ish dimensional vector to represent your patient. So that's one way. Or you can average them, like dimension by dimensions. Like you can add them all up and then divide by them for 3, for example, here. So that'll also be a nice way to derive or obtain patient representation vector. And again, as I said, if you use like transformer, or probably not transformer, if you use like recurrent neural networks, then you can feed arbitrary number of hospital admissions to RNN to derive or obtain patient representation vectors. So Yeah, RNN is a pretty flexible. I guess probably a go-to method when you're dealing with like sequence information like this. All right, so anyway, but if you're taking the classical approach, like logistic regression or support vector machine, you need to come up with a way to derive or how to aggregate these like information over like some number of years, like 10 years, into a single fixed sized vector, so that you can feed that vector into your prediction model. All right, so I guess that concludes the common preparation step for any machine learning model. So for any question or any like part that you guys want me to repeat in Korean? No? All right. We got about 15 more slides to go. All right, moving on then. So, okay, so because today we're only going to talk about classical approaches, so these are just examples of classical prediction models, or yeah, prediction and classification is probably the same thing in machine learning, like the numerical perspective or mathematical perspective. You either like you predict, for example, like if you're predicting readmission, then you either get it right or wrong. So it's kind of like classification. But anyway, so classical models examples are logistic regression. There are support vector machine. Decision trees are very hot. I mean, it's very popular in medical domains. K-nearest neighbors, ensembles like bagging, boosting, like gradient boosted trees, Bayesian networks. So these are all like very, very well studied models, and these were pretty like depending on which task or which domain you're talking about, they were all like popular prior to the deep learning era. So prior to like 2014, 2015, and still like they form a great baseline. Like some tasks can easily be done with logistic regression, for example, and some are very popular in the medical or clinical domains. Like logistic regression is very popular, and not just limited to medical domains, but like in a lot of areas. Decision trees are also pretty popular in the medical domains, probably because it's easy to interpret the model. Once you like learn the model, you can like study the structure of the trees and see how each feature or how like how the prediction or the classification is done. Basically, it's a very transparent model. You can just follow the trees and then see why. For example, if you're doing readmission prediction and you train a decision tree to predict ICU readmission or either hospital readmission, and then you feed in a vectorized form, like a vector representation, like I showed you before. You feed the vector form into decision tree, and then the decision tree gives you like yes or no, or like then you can follow like the routes that the decision tree has taken to derive at the final the decision, like yes or no. Like, so it's a very transparent model. And in medical domains or clinical domains, transparency, like or being able to trust your model or being able to interpret your model is very important, because you don't want to you can't just trust a black box model that might be doing some crazy thing within internally, and so the doctors or the practitioners won't buy the outcome, the prediction outcomes from a black box model. All right, so yeah, interpretability, we'll come back to that after we've covered the basic the deep learning methods, the basics of deep learning methods. Then we'll come back to how to make them, like the deep learning model, more interpretable. All right, anybody has any question with anybody not familiar with machine learning models here? I can't go into like too much detail because like it'll be another like semester, but I can just I guess I can touch upon the like high level concepts? No. All right, then I guess I'll move on. Okay, so out of all these different ways to different methods, different models, we'll just focus on logistic regression because it's probably the most popular model. So yeah, I guess not just in medical studies, but maybe in all statistical models studies. Like everybody, like this is like the go-to thing once you need to predict something, then logistic regression is probably a good choice to to start with. You don't want to start with like a humongous, like 100-layer deep learning neural network. You want to start with something simple. See if you can if the task that you want to do is actually predictable, at least to some extent, by very simple models. So it's a very well-studied model. I looked up on the Wikipedia and it says it was developed in the like 18-something, like 1850s or 1860s. So it's been around for like 150 years or something. And the once you've learned the logistic regression model, you can actually analyze the coefficients of the predictor variables. Predictor variable is the same thing as explanatory variable, independent variable, or features, like the variables that we looked at in the previous examples, like the ethnicity, marital status, gender. They're all like predictor variables. So once you convert your admission to like vectorized form and then train your logistic regression, then you can see how like the importance, or like kind of a relative importance of each feature to what you're trying to predict. So this is it's called logistic regression because it uses logistic function. So it's logistic regression is for binary prediction tasks. So it's either 1 or 0. Your outcome would be 1 being like yes and 0 being no, and it takes a mathematical form like this. So B is just the base for the logarithmic function. So it's like usually you use natural log. So it's an exponential e, natural number e. So, and this becomes your like multivariable like representation. So we'll just I'll just go into like step-by-step thing to see how this is derived. Like maybe a lot of you are already familiar with this mathematical formula of logistic regression, but I'm not sure if everybody's familiar with odds and log of odds and logits and stuff. So we'll go through that very quickly. All right, so odds. Is anybody like super familiar with odds or like log odds, or if everybody's familiar, I don't have to go through this, but if like this online thing is always really bad for like taking a poll or asking very simple questions. All right, I'll just go through it anyway. So it's probably very informative to like if somebody's like really familiar with odds and log odds, just I'm sorry about that. I'm sorry about going through this. And for everybody else, this will be like a nice refresher of how people have come up with logistic regression. All right. I've taken this material from this reference site, so this is a great, if you want to dig into like more in-depth explanation of logistic regression, please visit this website. So odds is something that converts your probability into a non-negative scalar value. So for example, your probability lies between 0 and 1. It could be 0.2, 0.5, 0.8, like 20%, 50% chance, 80% chance, whatever. Like you're doing a gambling, you're doing whatever. And odds is it's a ratio between actually being successful or actually winning the game and actually losing the game. So P being winning and 1 minus P being losing. So it's a ratio. So odds is a ratio. So if you have an 80% chance of winning, then your odds are 4. So you have you're 4 times more likely to win than lose. And if you have like 50% chance, if you have 50% chance, which is like random chance, then your odds of winning is just 1. is the same as losing. And if you have 10% chance of winning, then your odds are like very low. So and the odds, the value of odds sits between 0 and infinity. So if you have like, if your probability is 1, then the numerator will be 1 and the denominator will be 0. So it'll be like close to infinity. So this is the plot between the probability value and the odds. So as you like push towards the perfect like win probability, it'll like shoot up the sky and then like reach infinity. So you can see that the range of the probability is 0 to 1, but the range of the odds, I forgot like the domain and the codomain or something, like 정의역 and 치역, or was it something else? But anyway, so you're converting the value between 0 and 1 to 0 between the value between 0 and infinity. And then log of odds is you just take the log, you just put the log function in front of the odds. So that is why it's called log odds. And it is called logit. So it's a logit function. The logit function is putting a logit function on your probability is doing this operation basically. So again, this is now odds was converting your 0 to 1 probability to a 0 to infinity value. Now you're converting your 0 to 1 probability into a negative infinity, a value between negative infinity and plus infinity, positive infinity. So because you put log in front of like a non-negative value. So if you have win probability of 80% chance, then your logit will be like this. And then if you have a 50-50 chance, your logit will be 0. And then if you have like if a low winning probability, your logit will be a negative value actually. So as you go close to, as your odds go to 0, which means that your probability goes to 0, then you get the logit value of negative infinity. And then if you go if you get go closer and closer to the perfect chance, then your logit will be close to infinity. So the reason that we go all through this trouble of like converting probability to odds and odds to log odds is that a value between 0 and 1 is kind of like not so easy to handle. Like if you come up with if you're trying to like model the value between 0 and 1, it's like you can't use the entire range of like real value. You have to like cut it off between 0 and 1, and it's very like artificial, like continuous functions, like probability functions, to make them sit between 0 and 1. It's kind of unnatural. But if your probability value can be converted to some value that sits between like the entire real line, then that's like more manageable. So that's why we go through all this trouble. So okay, so logistic regression it's a regression of logit. Yeah, you're doing a regression using the logit function. So you want to model your logit function with a linear. You're linearly modeling your logit, basically logit function. So the logit of your probability, which is this, you are trying to explain them linearly with multiple variables. So x1 being like ethnicity, x2 being gender, x3 being admission types, x4 being like diagnosis, and all that. So, and the beta 0 is just an intercept. It's a bias. So what you're saying here is that I want to explain my logit function linearly as a linear combination between different variables, different predictor variables or features. And you can convert this like this. So it's a simple algebra. You put the log, you basically you take the log off, and then you get this, and then you do like you invert the numerator and the denominator, and then you get this basically. And then you put the p, you do like you shuffle the p's around, and then you want to get a single p, so you get this. And then finally, if you divide both the numerator and the denominator by this value, then you'll get this. B being E. So you can understand why it was initially written as a base of the log, because log you could take, it doesn't really matter here, it doesn't really matter which log you use. It could be log of 2, it could be log of 3, it could be log of it could be a natural log. It doesn't really matter, because all you want to do is you want to convert your probability value between 0 to 1 to a value between negative infinity plus positive infinity, and doesn't matter which base of which log you take. Like log of 2 will also give you this. Log of 3 will also give you this. Log of natural log will also give you this. Doesn't really matter. But just for because natural log is easier to handle, people just take natural log. So that's why this becomes like EXP, and this is not 2 or not 3, but the natural E. So, okay, so that's how you arrive from the probability. That's how you start from probability and then arrive to the logistic regression modeling. So as I said, this is a linear model. Yeah, at the very beginning there was like quiz 0 to give like one example of linear model, one example of nonlinear model, and some people have written down logistic regression as a linear model, which was a correct answer. Okay, so right, and yeah, so this just a simple mathematical manipulation. This here is actually you can convert them into a vector form and write them as an inner product. So these x1, x2, like these different features, different predictor variables can be seen as like a very long vector of a single vector like x. And if you look at the beta as theta, just simple like a manipulation, you just change the notation from beta to theta, which is the parameter or the weights of your logistic regression function. Then you can write this as this. So this theta, it becomes this particular form becomes like a theta transpose the x vector, and this will represent that given an x feature, given like an input, it represents the probability that your outcome will be like a true probability, like a winning probability, the chance of winning. Actually, y being 1 is like winning, and y being 0 becomes like losing. So, or in our case, readmission case, y being 1 is actually being readmitted, and y being 0 is not being readmitted. So actually, it's not a win. Being readmitted is a bad thing. Anyway, so you see what I mean. So this function will be our logistic regression function, and because now this is a vector, you can see that this is exactly like this. So we've gone through all the trouble of converting your hospital admission into a single fixed size vector of 40,000 dimension-ish, like 40-something dimension, 40-something thousand dimension. And the reason we did that is because this is a vector, so now you can plug in this very, very long vector into X, and that means that you need to also that means that this theta is also 40,000 something dimensional vector. And here, so, and we need to learn it basically, because in order to correctly predict for the given X, for example, in order to correctly predict the readmission probability given the readmission admission representation vector X, you need to have a proper value for these thetas, and you need to learn them from data, learn them from the data, training data basically. So, all right. And how you learn it is typically you use something called maximum likelihood estimate. So if anybody's familiar with linear regression, there's a closed form solution for linear regression, which means like you can analytically solve the form and get the and derive the values for the theta, the parameters, in a nice mathematical way. But for logistic regression, you can't do that. So the need to estimate when I say estimate theta is because you don't know theta, the true theta. All you have is this, and you don't know the true theta to make the correct prediction. So you need to learn that from data. So in order to estimate theta, you need to learn it from data, which means that you need to learn it from the training pairs. So you have like n number of pairs, where X is the record. It could be like hospital admission or ICU admission, something like that. So X is a record, and Y is the label, like whether that particular record that particular admission led to a readmission. So like y being 1 is yes, that patient was readmitted. Y being 0 was no, that patient was not readmitted. So you have a lot of pairs, basically capital N number of pairs of X and 1. And so you need to estimate the theta from the training pairs, and the way you do it is something called maximum likelihood estimate. And in order to understand what that is, you need to first understand what log likelihood function is. And the likelihood function, so you have, this was just copy paste from the previous slide. So you have this function, probability function or logistic regression function, that looks like this. So this represents the, as I said, given a data, given a patient record, this represents the probability that that patient will be readmitted. I'm just, just coming to this, I'm just using the readmission prediction task all the way. So, and if you have this, then the likelihood function would likelihood function based on your training pairs. You can't have a likelihood function without the training data. So once you have the training data, you want to have a likelihood function that looks like this. So this is a probability function given the ith example and ith example. So xi pair, xi and yi pair. So you have a pair, like a lot of pairs. So this is the ith pair, and you have the probability function, and you have, because you have ith pair and they're all independent. Like the first example, second example, third example, they don't have anything to do with each other. Like they're all independent examples. So you can multiply them all together to get your likelihood function, and a single probability function will look like this. This is basically a Bernoulli distribution. It follows a Bernoulli distribution because you either the patient is admitted, readmitted, or not readmitted. So it's a binary event, and in order to model a binary event, you use Bernoulli distribution, and so that is why you represent this as a Bernoulli distribution. So you have maybe I should just go to Bernoulli distribution. Bernoulli distribution. So here you can see what is that is weird. Okay, so basically, so this is your mathematical, like a probability formula for Bernoulli distribution. So k being the label here, here the yi is our label, either readmitted or not readmitted. So k is the same thing, and p being the probability. So our probability was modeled by this function, the h theta function. So that's why you write h theta here. So this p k 1 minus p 1 minus k is exactly the same thing here. So it's Bernoulli distribution. So you multiply all these into, like, because as I said, these are all independent samples, so you can multiply all of them in a chain, and then because they're all probabilities, once you multiply a lot of probabilities, it'll quickly go to 0, because like 0 point, like if they are all like 10% chance of, like, I don't know, occurring, then that means like 0.1, and you multiply like 1,000 examples, you multiply 0.1 1,000 times, that's like, I don't know, like very, very close to 0. So it's easier to handle likelihood function with a log function in front of it. So this is a likelihood function, L theta. So likelihood function is a function of theta. So you're given a fixed examples, and you have a function of theta, the learnable parameters. So this is L theta given X, and then you put the log function in front of it to make it more like manageable. So you put log here, and then the multiplication will become like summation. So log, so like you put log in front of here, then this becomes this, basically. Now it becomes a summation, and you want to do, like, you want to average them out, because you're summing like n training pairs, so you want to average them out. So that's why you divide the entire thing with the same number, with the number n. So this becomes your log likelihood function. So, and this basically tells you that the likelihood of seeing this data, actually you observing this data with given parameter, like you have to start somewhere, because you don't know the true true theta in the beginning. So you start somewhere, and that somewhere is like some random number for the theta. And given using the theta, that this tells you that the likelihood of seeing your training data with the theta, basically. So, and you want to maximize your the log likelihood, meaning that you want to learn the parameter theta such that the probability of seeing these training pairs is maximized, because these are real pairs that you see from the real world. So you want to learn the theta such that you actually maximize seeing these probabilities according to these like distributions and this logistic regression function. So basically you want to maximize this, and the maximizing log likelihood function is the same as like minimizing the negative log likelihood function, because you put the negative sign here, like minus sign here, and then you minimize it. That's exactly maximizing this, right? So that's where all the like negative log likelihood NLL comes from these like deep learning era these days. Everybody's using negative log likelihood for in like NLP. That's where this thing comes from. So you minimize the negative log likelihood using gradient descent iteratively. You're like doing like you do this like iterative fashion. Okay, so I think we're out of time. So we have a couple more slides for like evaluation, but I guess we can talk about that in the next Thursday, and then jump into the deep learning stuff after that. So all right, any questions so far? It's already 10:31. So if anybody has like quick question, I can answer that. Otherwise, you can post them on Classroom or send me or the TA's emails, and yeah, and I'll try to address that as quickly as possible. All right, maybe is what I'm teaching like too easy for everybody? Like any feedback would be nice. Like I'm not sure if I'm wasting time just going through all the like basic steps, because maybe everybody already is familiar with all these. So this was just a waste of time. So if you have any feedback, just don't be shy to share them. I think there was okay. Not easy for me. Okay, that's good. So, I mean, I'm sorry, but I can't go easier than this. Otherwise, this will be like a machine learning class, and I'll be talking about these stuff for like the entire semester. But these are like the absolute essential stuff that you need to be familiar with in order to progress to the next stage. So if you have any question about the material today, just shoot me an email, or we can talk online 101 after this class. So anytime. Yeah. Is there a website where the lectures and slides are? Yes. Oh, so I guess Mr. G only came a bit, is a kind of a newcomer. So there's a website called Classroom where I upload all the videos and where I upload all the slides. So I'm sorry. So anybody can leave. Like if they're in a hurry, anybody can leave. I'll just post the Classroom the access information to Classroom on the chat box. I'll use my time to review recent lectures. Okay, sure, you can do it. Please go ahead, do that.